So in this presentation, I'm going to talk about buffer overflow attacks. Now this happens to be something near and dear to my heart since at least half the time I'm writing in the C or C++ languages. And these are especially vulnerable to buffer overflow attacks. So first, what is an exploit? Well, an exploit is any input that takes advantage of a bug, glitch, or vulnerability in order to cause an attack. An attack is an unintended or unanticipated behavior that occurs on computer software, hardware, or anything electronic, and that brings an advantage to the attacker. So now let's talk about buffer overflow attacks. One of the most common operating systems bugs is buffer overflow. This is when the developer fails to include code that checks whether an input string fits into its buffer array. An input to the running process exceeds the length of the buffer. The input string overwrites a portion of the memory of the process, or causes the application to behave improperly and unexpectedly. So what are the effects of buffer overflows? Well, the process can operate on malicious data or execute malicious code passed in by the attacker. If the process is executed as root, the malicious code will be executing with root privileges. So now let's talk about address space. Every program needs to access memory in order to run. For simplicity's sake, it would be nice to allow each process, that is, each executing program, to act as if it owns all of memory. The address space model is used to accomplish this. Each process can allow space anywhere it wants in memory. Most kernels manage each process's allocation of memory through the virtual memory model. How the memory is managed is irrelevant to the process. So here we have a model, an image that kind of lays this out. So on the left, you see what the program actually sees. There are 1, 2, 3, 4, 5 blocks, but they actually map into memory in a different order. As you can see, there's no relationship to the actual memory in memory and what the program thinks the memory is. Okay, and the hard drive illustration here is because many times memory is swapping in and out of the hard drive using virtual space. So let's talk about Unix address space. Text is machine code of the program compiled from the source code. And if you've had any programming languages such as Intro to C here at UCF, then you have this concept pretty well. There's data that's part of the static programs, and this includes variables initialized in the source code prior to execution. So BSS stands for block started by symbol, and these are static variables that are uninitialized. The heap is something you actually really need to pay attention to for Stack Overflow. This is data dynamically generated during the execution of a process. So if you had Intro to C, this is the same as malloc. When you use a malloc to allocate memory, or in the C++ language when you use new to allocate new memory, it comes from the heap. Stack is quite a bit different. This is a structure that grows downwards and keeps track of the activated method calls, their arguments, and local variables. So stack actually is a multi-purpose. It's got local variables, it's got return addresses, and things such as that. So now let's talk about vulnerabilities and attack methods. So here are some vulnerability scenarios. The program may have root privileges and is launched from a shell. The program is part of a web application. So here we have the typical attack methods. The first is to find a vulnerability. The second is to reverse engineer the program. And the third is to build an exploit. So here's a buffer overflow attack description in a nutshell. They were first described in this on this website in an article called Aleph 1, Smashing the Stack for Fun and Profit. Sounds like a pretty interesting article to me. And notice that this goes back to 1996, so this is not a new phenomenon. Next, the attacker exploits an unchecked buffer to perform a buffer overflow attack. Then, the ultimate goal for the attacker is getting a shell that allows to execute arbitrary commands with higher privileges. The kinds of buffer overflow attacks are heap smashing and stack smashing. And of course, that has to do with heap is when you're allocating memory off of the using malloc or new. Stack is when they're like local variables. So here's actual code that helps you understand what a buffer overflow is. Notice in this C code, domain.c, you have two variables that are char arrays, char buffers, var1 and command. Okay. Now, if you string copy who is into command, you're fine because you string copied 5 characters. Actually, it's 6 characters because the null terminator actually gets copied into command. And then the string concatenate, whatever the person typed in on the command line is concatenated. So it might be who is, blank space, blah, 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 whatever. So the problem here is that the command typed in could be very, very long. If it was very, very long, it might exceed the space that the buffer has. So here we have a string copy into var1 of also the command line argument. Here again, it could easily overrun that buffer. So it could actually overrun both buffers if the command line argument is extremely large. Okay, and that's sort of the gist of these. Now, note that var1 and command, those arrays, those are stack variables, or excuse me, those are allocated off the stack. As we talked about, those are local variables, so they come off the stack. Malloc or new weren't used to allocate them, so these are stack variables. So the string copy vulnerability happens when you're going to overwrite something that doesn't have enough space. Let's say I typed in as a command line argument something like supercalifragilisticexpialidocious. Well, obviously that's way larger than the var1 buffer, and it would exceed that by quite a lot. Also, when I did the string concatenation after the command, into the command after who is, and then that would exceed that buffer also. So notice argv1, that's the command line parameter that the user typed in. And note, in the C language, argv sub 0 is the actual program name. That's just a little bit trivia for you. But this first string copy doesn't even check the buffer, doesn't check to see how much space it has left, doesn't check to see how much space that the command line argument has. The concatenation also doesn't check. So those are the two vulnerabilities, the string copy and the string concatenation. Okay, this is showing you kind of how it goes. You see how the argv1 got copied into, let me back that up just a bit. Okay, so here you have var1 as 15 characters, right? Okay. Okay, so it's 15 characters, that's all you've got. But now, what if you try to copy in too much? It's going to overrun that into command. Okay, in command, you've overflowed into command. Okay. And you might have inserted an exploit into command, and if so, then you can run the exploit. So string copy versus string ncopy. String copy copies whatever is in the string into the second argument and the first argument. So whatever's there, it copies. If the source string is greater than the destination string, the overflow characters may occupy the memory space used by other variables. The null character, as I said before, is always appended at the end automatically. So there's always going to be one more than you think it is. So for the answer, my name is Rick. So if I string copied RICK, it would actually be RICK null terminator. So it would be 5 characters. String ncopy actually copies the string by specifying the number of n characters. So you are actually copying n characters. So this is actually going to be a lot safer. If the source string is longer than the destination string, the overflow characters are discarded automatically. You have to place the null character manually. So here's return address smashing. So you make a system call to fingerd, which runs as root. Okay, you write malicious code into the buffer. Okay, so you can write anything into the buffer if you're doing it from a command line or something. So you write malicious code into the return into the buffer, and overwrite the return address to point to the malicious code. So here you have a buffer. Now you got your malicious code, and where the return address was, you overwrite that. So it is now going to, instead of returning to wherever you came from, it's going to go ahead and execute this malicious code. When the return address is reached, it will now execute the malicious code with the full rights and privileges of root. Okay, Unix shell command substitution. The Unix shell enables a command argument to be obtained from the standard output of another. This feature is called command substitution. When parsing command line, the shell replaces the output of a command between back quotes with the output of the command. So an example, file name.txt contains string farasi. The following two commands are equivalent. Finger cat name.txt, finger farasi. So now let's talk about shellcode injection. An exploit takes control of attacked computer, so injects code to spawn a shell or shellcode. A shellcode is code assembled in the CPU's native instruction set. It's injected as a part of the buffer that is overflowed. It's similar to what we just talked about 2 slides ago. We inject the code directly into the buffer that we send for the attack. The buffer then containing the shellcode is a payload. So how do you mitigate buffer overflows? We know how a buffer overflow happens, but why does it happen? Well, this problem could not occur in Java. It is a C problem. That also applies to any .NET language such as C# or Visual Basic.NET. Also, if you're using C++ managed code, which is another .NET language, it can't happen. But C and C++, native C and C++, it definitely can happen. In Java, objects are allocated dynamically in the heap. Also cannot do pointer arithmetic in Java. In C, however, you can declare things directly on the stack. So one solution is to make the buffer dynamically allocated. That would be using malloc in C or new in C++. Another operating system problem is that fingerd had to run as root. Just get rid of fingerd's need for root access, and then the program needed access to a file that had sensitive information in it. A new world readable file was created with the information required by fingerd. So now let's talk about stack-based buffer overflow detection using a random canary. Okay, and if you're using the Microsoft C and C++ compiler, this is actually a pretty common thing to do. So here you see a buffer, local variables, and canary. Canary is a random number. However, in the Microsoft runtime, it's a hex CC repeated over and over and over again. So if you do a buffer overflow attack attempt, and it corrupts, say, the data and then the return address, the canary is placed in the stack prior to the return address. So any attempts to overwrite the return addresses also overwrites the canary, and you can tell. And fortunately, the Microsoft runtime takes care of this for you.